Welcome everyone. Today we are exploring one of the most critical vulnerabilities in modern software, the buffer overflow attack. I am Salih, and I will be taking you through the foundation of this threat. Our digital world is built in code, but with this power comes incredible risk. Every day, cybersecurity professionals face a sophisticated attack targeting the very core of how computers manage memory. One of the most dangerous and foundational vulnerability is the buffer overflow attack, a threat that strikes at the heart of the system memory management. So, let me explain what is a buffer overflow actually is. Imagine pouring too much water into a glass. It does it doesn't just sit there filling the glass. It spills over and corrupt whatever is nearby. That is exactly what happens in a buffer overflow. In technical terms, a buffer overflow occurs when a data exceeds a memory buffer limit. This overwrites nearby memory locations, creating a critical vulnerability. The attacker sends more data than the buffer can hold, and this excessive data spills over into adjacent memory areas containing important information, like return address or system data. Well, of course, there is a root cause. Well, where does this vulnerability comes from? Language like C and C++ provide a direct memory access, but which is powerful, but they do not automatically check memory boundaries. They don't know where is the first, where is it start, and where is it end. This structural feature is what creates the potential of overflow. Well, the consequences, attackers can exploit this in three escalating ways. First, they can corrupt data causing program malfunctions. Second, they can crush the entire system. Worst case, they can execute their own malicious code and take complete control of your system. This is why understanding the defense is so critical. Now let's explore how modern systems fight back against these attacks. Well, we have a lot of defense mechanism. The first one is ASLR, which is um, a modern system employ three powerful complementary mechanisms to prevent power overflow attack. The first is ASLR, address space layout randomization. Think of think of it this way. Imagine the fortress constantly rearrange its internal layout. An attacker might have a map showing where everything is located, but with each but which but with each attempt, the map becomes obsolete because the layout has changed. How ASLR work? ASLR is a kernel defense that randomizes the memory address of key data regions, the stack, the heap, and shared libraries. Here is why this is brilliant. Well, in old systems, these memory addresses were static and predictable. An attacker could study a system, learn the stack is always at memory address, for example 0x um, AAA, the heap at 0x BBBB, and libraries so on. With this knowledge, they could craft an attack using a hard-coded address, but with ASLR enabled, every single time a program runs, the memory layout changes. The stack might be at 0x and heap at 0x triple y and so on the libraries. Run 2, completely different address again. Run 3, different again. This randomization makes it extremely difficult for attackers to predict where their malicious code will land or find specific targets. The attacker's carefully crafted exploit fails because their assumption about memory locations were wrong. So ASLR makes it hard for the attackers to find their target. So next, My friend will explain the method number two. Thank you very much.
Hello everybody, I am Abdurrahman Bereket and I will continue explaining these slides. So even if an attacker bypasses ASLR, there is a second line of defense, data execution prevention or DEP, which relies on the NX bit, which means no execute bit. Here is the analogy. Certain zones of the fortress are strictly marked as no combat zones. Even if an attacker successfully smuggles a weapon, malicious code, into these areas, they simply cannot use it. The fortress will not allow weapon to be used in data areas. DEB is a defense that prevents the execution of code in memory region intended only for data storage. It relies on a hardware feature called the NX bit, the no execute bit, which marks pages of memory as non-executable. Here is the flow when an attacker tries to inject malicious code. First thing, attack phase. The attacker injects malicious code into a data memory area, typically the stack. Next, execution attempt. The CPU tries to execute code from this address. Next, hardware check. The CPU checks if the NX bit is active for this memory page. Next, the answer is yes. This is a data page, not code, so execution is denied. So the program terminates safely, preventing the hijack. This is a hardware enforced protection. Even if the attacker gets their code into memory, the CPU itself refuses to execute it. It's like having a physical lock that prevents weapons from being used in certain areas. DEB, uh, so in summary, DEB prevent the attacker's smuggled code from running. Now, what if we want to catch attackers in progress before they can cause damage?
Hello, Doctor. In this slide, I will explain how stack canaries detect and stop buffer overflow attacks step by step using the diagrams shown here. First thing, we look at the first image at the top. Here we can see here we can see a simple buffer overflow example. On the left side, the memory is before the input is giving everything in is saved. On the right side, the program receives input that is larger than the buffer size. Because the input of them is too large, the extra data starts to overflow into nearby memory. This overflow, it will be it starts to overwrite important values stored next to it in the stack. Is every is This is the very dangerous because once important values are overwritten, the attacker may control the program or some kind of that too. Now we finish it in the first picture. Let's move to the second image in this middle, which shows the normal stack slow out with a stack canary. At the room, at the I'm sorry, at the bottom, at the bottom we have the buffer where user input is stored above the buffer. We have the canary value and above of the canary we have the frame pointer and the return addresses. The stack canary is a secret random value placed between the buffer and the return address. During normal execution, this value must remain unchanged. There is the reason it's placed here is a simple, which mean this one, the simple any overflow coming from the buffer must pass through the canary before reaching the return address. This one here, the buffer, these arrows show the direction in which the overflow would move if the buffer receives too much input. The data receives upward and first hits the canary. So the canary works like a kind of work, I mean, uh, like you can say in this part. So the canary works like a warning barrier between the user and data and the critical control data. And this one in the down, when you see it now, it's, I'm sorry. When we come then the last image, or we move the last image at the bottom on the left side, we see the attack before the attack. Everything is in correct place. The buffer contains normal data and the return address is saved. On the right side, we see the stack. We see the stack after the attack. Here, the buffer, it will be like the buffer overflow has overwritten important values. The return address is no longer the original one. Instead, it now points to malicious code. This means the attacker has successfully taken control of the program execution. But this is exactly the situation that stack canaries are designed to prevent. When when a function is about to return, the system automatically checks the canary value. If the value is still the same, the program continues normally. But if the value has been changed by an overflow, the system immediately knows that an attack has happened. At that moment, we can say the program is terminated before the return address can be used, so the attacker never gets control of execution. So in summary, we can say a stack canary is a detection mechanism. It does not stop the overflow itself, but it detected the memory corruption at the exact moment it happens. By checking the canary before returning from a function, the operating system can stop the attack in real time. This is how attackers protect the stack from buffer overflow attacks by detecting any unauthorized memory modification before it becomes dangerous. Thank you, sir. Thank you, Doctor, for your listening, and I hope it will be I explained in a safe way. Thank you for everything.